Okay, good morning, and I'd like to thank Andrew for inviting me today to give this talk. And he asked me to give a tutorial on nanotechnology, which means it has to be very, very basic, okay? But nanotechnology is such a big topic, and I'm only giving 15 minutes, so it'll be really difficult to cover the whole field of nanotechnology. So I'll just give you a very brief, basic introduction to nanotechnology, and hopefully convey the message that nano is actually quite useful for big things, okay, including solving energy problems that's facing the world today. And so the first thing is, what is nanotechnology, right? So nanotechnology is really anything, it's a science and technology about anything that's below about 100 nanometer in size, right? And if you're not familiar with how big is 100 nanometer, the size of a human hair is about 100 microns, okay? And a micron is about 1,000 times bigger than a nanometer, okay? So nano is really, really small. And when you think about nano, normally you think about things like nanoparticles, okay? So particles that's really, really tiny. And also there are a lot of nanomaterials that's actually one-dimensional, such as carbon nanotubes, right? So a nanoparticle would typically be about 2 nanometer in size, up to about 20 nanometer, 50 nanometer. And a nanotube can be, the diameter can be as small as 1 nanometer, but the length can be a little longer, right? It can be microns, or sometimes can even be millimeters or centimeters. So nano is really materials with at least one dimension that's below 100 nanometers. Okay, so that's really what nanotechnology is about. And now when you think about energy, at least I think about energy, when I think about the energy, I think about the sun, okay? So, the energy on Earth is really all coming from the sun. And the sun is really, really huge, right? So, actually, if you measure the size of the sun by nanometer, okay, so this is how many nanometer you have for the sun. So the sun is 10 to the 18th nanometer. So it's a huge subject. And so the question is, do they actually have any relationship? Can we use nanoscale materials to do something good, to utilize the energy of the sun? Right, so this is actually a very active topic going on right now. All right, so let me talk about briefly what is nano. Now we talked about what is nano. Now let's talk about why we care about nanomaterials. And this is a crystal that's big, okay, that you can find in the field. These are huge crystals. But people have been making these crystals that's into much smaller sizes, such as the one here. The scale bar here is only 2 nanometer. And the reason that people do this, make them small, is actually because the physical property of these materials change as you make the size of the crystal smaller, okay? So this is a good example of that, because you see as the crystal reduce in size, right, increase in size, 2 nanometer to 5 nanometer, the color of the material actually changes, okay? And that's really interesting property. And the reason for that is because the property change as size reduces. And one of the property of matter is what is a metal or semiconductor. And so in this case, the so-called band gap for the semiconductor actually increase as the size reduces. So by simply changing the size, you can tweak the property of the material, which could be useful for different applications, right? So this is a very, very important science, a piece of nanoscience. And another example I'll give you is carbon. Okay, carbon, as you know, in your pencil lead you have graphite, and that's a piece of graphite, and you use it every day to write. And now this is a three-dimensional crystal, but you could think of making it a two-dimensional, right? Just taking a sheet of graphite, and that's called graphene. So this is a single atom thick layer that has all the atoms exposed to the environment, which could be useful. Okay, there's a huge surface area. Or you could take the sheet and roll it up into a cylinder, then you make a carbon tube, right? So as you do this, as you go from three-dimensional to two-dimension to one-dimension, you actually change the physical properties. So the properties of that versus this are all different. Okay, so it's a simple change in size that changes the physical property of these materials. And so my group, as Andrew mentioned, works on these materials, and the features of these materials are as follows. They're small, they have high surface area, and they're actually very good conductors. Okay, they conduct electrons really well. And another thing is that they can actually turn into semiconductors. So this sheet is a metal, okay? But if you make a tube that's small enough, it actually becomes a semiconductor. And semiconductors are important, right? It's useful in transistors, in computers. It's useful for solar cells, right? So this actually can become a new type of semiconductor. And they can actually emit light. If they're semiconducting, they can emit light. They're fluorescent, which you can actually use for biological applications, which my group works on. And they're also very mechanically strong because carbon-carbon bonding is very, very strong. Okay? Okay, so just to summarize, the hallmark of nano is really listed here. There are many, many different properties, but these are the most central and simple ones. One is that the property can change simply due to size, getting small. And these are a perfect example. One is the melting points actually can reduce. So a tiny particle has a lower melting point than a big crystal, okay? Because atoms on the surface are easily mobile and they can melt much more easily. And metals can turn into semiconductors or insulators as they become small, and band gap increases. Okay, all of these are due to quantum mechanics, which I won't get into. The chemical property can change too. The bonding at the surface is weaker. Atoms on the surface are less bonding than atoms in the middle. So they're weaker bonding, and as a result, they're more reactive chemically. Okay, you can do chemical reactions more easily to nanoscale materials. Okay, now let's talk about why they're beneficial, how can they be used, right? How do you benefit from them? And these are, again, simple summary of what they're good for. One is faster, okay? So because they're smaller, so there are smaller distance to travel for the electrons, for the ions. So you can get devices that's faster, lighter, okay, because they're small. And because they're small, they can be densely packed. So you can have a lot more on the same area. And cheaper, hopefully, okay, at least for some of them. And then they can also give you properties that you don't normally get so that you can make new type of devices. And the best example I can give you about this benefit of nano is in the area of electronics, okay? I don't know if you guys know what this is. This is actually a transistor, the world's first transistor made in 1947, okay? So at the time, a transistor looks like that. It's very large, right? And now these transistors are in our laptops, okay? Millions of them. Okay, so imagine you build a computer with that, right? And people have done that. So people have built the first computer using 30 large transistors, okay? And can you imagine using a computer like that, right? And you know, this is what computers look like now. You can put it on your fingertip, right? Imagine Steve Jobs do that to this computer. And the reason he can do this is because now computer chips are so small and transistors are so small. This is one transistor now. You know, the size of it is only, you know, this is 20 nanometer. Okay, so this is replacing that. Therefore, this is replacing that. Okay, so you definitely see the benefit of denser, faster. The computer is much faster, lighter for sure, cheaper. Okay, so Nano can really revolutionize different fields. It has done that to electronics, but can it do the same thing to energy? Right, so there are a lot of challenges in energy. I'm sure you have heard about this through this workshop. You know, right now we're using fossil fuels and we're, you know, getting all those steep increases in fuel prices. So the question is, can we use renewables, right? So there are all these renewable sources, but the key one is really the sun, right? So the question is, can you harvest the energy better, okay? Especially the solar energy. Can you convert them into electricity, into chemical energy, or other sorts of energy, and then can you store them better? And how does Nano plays a role in this area? So the question is, can Nano help energy? So again, that's the sun. And to harvest the energy of the sun, you need solar cells, okay? So can you make better solar cells? And the sun, the energy from the sun is intermittent, so often you want to store that energy somewhere, so you need batteries, right? So can you make better batteries using nanotechnology? And another type of major source of type of device is actually fuel cells, okay? So basically, the energy from the sun can also turn into chemical energy. For example, you can split water into hydrogen and oxygen, right? Then hydrogen can be used as a fuel, and it goes into driving a car, right? So you need to make the better fuel cells. Can you do that? And then, in order to make the fuel cells to work in a car, you need better ways to store hydrogen. And now Nano can definitely help in that because Nanomaterials has a lot of surface area, so you can pack a lot of hydrogen molecule into this material so that you can carry hydrogen around. So applications and devices like this are, you know, there are a lot of similar ones like this here that all need solutions, okay? So I think Nano can help, okay, to utilize the properties of these materials as I mentioned in the beginning. And I'm going to just use battery as an example because my group does some work in this area. And so I'm sure you've heard or maybe even driving an electric vehicle already. And so these are purely electrical vehicles made by different companies. One of them is across the street in Menlo Park. And so you see the, you know, they're very nice, right? They don't use any fuel other than electricity from the battery. But the problem is they don't drive very far, okay, after a single charge. Or they can drive further, but becomes very expensive, okay? So clearly you need better batteries in electrical vehicles. Not only in electric vehicles, you also want better batteries in your laptops and cell phones as well, right? So batteries are extremely important. And so here's a plot of how energy storage works these days. It shows different kinds of devices. One is a supercapacitor. This is a device that basically stores charge like a capacitor. And the good thing about it is it's very fast. Okay, you can charge and discharge very quickly. Therefore, this power density you see here is very high. So that means you can really charge or discharge in a matter of seconds or minutes. That's extremely good, right? But the problem is the energy density is low. Okay, so that means you cannot run your laptop or your electric vehicle for very long. Okay, then you have to recharge it again. The other type of device is a lithium-ion battery, which you use in your laptop. And these devices, you see, have higher energy density, meaning you can use your laptop for hours and hours. But the problem is that they're slow. Okay, the charge and discharge take a long time, which I'm sure you have experienced. You have to put your laptop there to be charged for hours to use it again. Okay, so the question is, can we do better? Right? Can we make batteries to be fast, like a supercapacitor? Okay, so have powers to be around here, and then have energy densities like batteries, lithium-ion batteries, right? Up there. Okay, or go even further. Okay, so can we do that? So I want to tell you a story, a piece of work did in my group recently that has to do with this gentleman. I don't know how many here know who this is. Yeah? Anyone? He's the inventor of the light bulb. Yeah, that's Thomas Edison, who actually lived here close to us about 100 years ago. And he invented the light bulb, which is the most famous invention, but he also invented a battery called nickel-ion battery. Okay, it uses two electrodes. One side is nickel, one side is iron. Actually, nickel hydroxide and iron oxide. Okay, and it's a very old battery. Okay, it's got very good energy density. Okay, it's like a battery. Right? You can store quite a bit of energy, and it's quite safe. Okay, it works in water. So the electrolyte in this battery is actually water instead of organic electrolyte, which are typically flammable, right? This is why the Chevy Volt caught on fire some time ago. And it's because the electrolyte, the organic solution in the battery actually caught fire. But this is water. Okay, so it's going to be very safe. It's not going to burn. And it's slow. Okay, it takes hours or even overnight to charge it. Okay, but that's about 100 years ago. And this is actually a photo of Thomas Edison with his favorite battery in his hand. Okay. Now, how did he make that battery? Well, this is a conventional way. You mix this nickel hydroxide with some carbon particle, okay? And these particles are not even nano. They're very large particles, okay? So that's how conventionally you would make a battery material. And the way we make these materials is by growing very small nanoparticles or plates onto graphene, okay? So this is a very high surface area material, and it's a very good conductor. And the particles are so small, so now they can actually transfer electrons to that sheet very quickly, okay? So this is a very efficient way to get electrons in and out of the battery, all right? So you're now using the benefit of nano. The small things travel very short distance, and they're very good for conducting electrons. So once you do that, you can actually make a battery. This is some data showing the sheet, the plate made on graphene, okay, like that. So once you do that, you can do this for both sides of the electrode, okay, and put it together. One is iron, one is nickel. And when you put it together, you can make a battery that runs very quickly. Okay, so this is the charging and discharge property. You see that the charging and discharge is very fast. Okay, this is in seconds. So this is a battery now that can be charged in about 2 minutes, and it can be discharged in about 10 seconds. Okay, so now you have a battery you could charge very quickly, and also you can also discharge it very quickly. All right, so this is exciting because of potential usage in electric vehicles. And in fact, people have made electric vehicles more than 100 years ago using the Edison battery. Okay, this is an example of it, okay? And people actually have driven 1,000 miles with it in some sort of competition to show that it actually works. But the trouble back then, of course, is it's slow, takes a long time to charge and discharge. Right? Imagine charging a car overnight, then you have to wait in a motel somewhere, and then you can drive the car away. Right? So the dream here that we and others are pursuing is, after such a long time, can we make electric vehicles now that runs a long distance after a single charge, and then you can be recharged in 10 minutes or so, like you go off the highway to a gas station and be ready to go again in 10 minutes. Okay, so that would be extremely nice if this happened. We're not there yet, but it's definitely an exciting direction to go. All right, so I'm running out of time. So let me summarize. So hopefully I conveyed the message that you can make things that's faster, like in the computer case, also in the battery case. Lighter, definitely in the computer case. They can be packed much more densely, cheaper. Your laptops are getting cheaper. And you can definitely get more better devices and more advanced properties, including the example I gave you, which is the ultra-fast battery. Okay, so these are the students and postdocs and undergrads who did the research in my group, and thank you very much.
We've got 5 minutes now for a Q&A.
I understand why you want to charge a battery quickly, but what is the benefit of discharging?
Okay, the discharge is really something you can control. You don't have to discharge it so quickly. You could discharge it slowly and let it run for a longer time, but the amount of energy will be the same. There are some cases you actually do want to discharge it quickly, like when you are driving a car, sometimes you need a lot of acceleration. And that's when you also want to discharge it very quickly. But there's nothing stop you from using it slowly.
Is there research going into supercapacitors to regulate the discharge so that they can last longer?
Supercapacitor is a very active field, but the fundamental problem is it's basically a capacitor. Okay, and there's only that much room you can increase the surface area to increase the energy density. So it's really, really hard to increase the energy density to be higher than what it is now. Because the batteries definitely give you more energy density. But the key is the supercaps are really good because they are very safe. They use, well, at least for the ones that works in water. And they can be charged and discharged very quickly. So it'd be really nice to combine the speed of supercapacitor and the energy density of lithium-ion batteries, or even better batteries, so that you're both fast and also have a lot of energy that lasts a long time.
Is there an optimal size that researchers have agreed upon for the size of the nanotechnology that goes into building solar cells? Because when we were talking about the quantum effect and how you could reduce the size and to increase the amount of energy that it absorbs, is there not like an agreed upon size?
Okay, so you're talking about solar cells. Okay, so as you know that in order to absorb the solar light, the sunlight, you need to cover the solar spectrum, right? Which goes all the way from UV to infrared, actually. So there's no one size that's gonna absorb all this light, okay? So in this particular case, you actually need a variety of sizes that has a variety of band gaps so that it can absorb all the light, okay, to get the most efficiency out of the conversion.
So as we all know, the cell phone battery is kind of a barrier now for smartphone development. So when do you think is the next kind of big revolution for cell batteries?
For the cell phone batteries? The cell phone batteries right now uses a lithium-ion battery. And lithium-ion batteries basically uses two electrodes. Right now, one side is graphite. The other side is something like lithium manganese oxide. Okay, so every time when you want to have a boost in energy, you have to change at least one of the electrodes with much higher energy materials. And I think one material for the graphite side, the anode side, people are working on is actually silicon. Okay, silicon actually has much higher energy density than graphite. And but there are a lot of problems. Okay, for example, silicon would expand a lot during the operation, which can destroy the battery. So people are actually doing nanotechnology to engineer silicon electrode to solve these problems. Professor Yi's group here at Stanford actually works on that problem. And I think there are companies working on this as well. Silicon. So if this works, then you will get about a 30% increase in energy density. So that means your laptop will run, or cell phone will run 30% longer, which would be actually a quite big jump. But I think at least it will still take a few years for that to happen. So that would be the closest thing, I think, in terms of making better batteries for cell phones.
Can you touch briefly on what it takes to produce something that's on such a nanoscale? So, like when you're trying to make a carbon nanotube, you can't just roll up a tube, I think. What goes into that?
Okay, so to make, let me tell you how to make a graphene first, right? So how we make our graphene. Obviously, you cannot, at least at a large scale, you cannot use a Scotch tape to peel off graphene, which did win a Nobel Prize a few years ago for physics studies, but you cannot do that for making batteries. So what we do is actually we take graphite powder, which you can buy at very cheap prices, and then we split the sheets away. Okay, we find chemical ways to split the sheets from one another so that it goes into a solution. And then we use chemical methods to make these nanoparticles on these graphene sheets. And these are relatively cheap and simple chemistry processes. And the cost is also quite low. Okay. And for nanotube, it's a little more complicated. You actually have to use like a metal particle as a seed, and they grow a tube from that particle, okay, in the gas phase. So you need a furnace of some sort to do this kind of production. But people have engineered systems to do that. And nanotubes, though, the cheapest ones you can buy these days is probably $10 a pound or something like that. People can actually produce them at the ton level already for carbon nanotubes. It's still a little expensive than you want, but it's definitely conceivable to make them into commercial products.
One more question. One last question. Please.
When do you expect to have the 1,000 miles to charge?
I hope next week, but yeah, the work we're doing, we did do a demonstration that you can charge very quickly and discharge very quickly, and the energy density is also very high. That's all good. So the next step is really to scale it up. Okay, right now the material we're making is like 100 milligram each time. Okay, and to make a small battery. right? So you definitely need to make that material, the same material at the kilogram or even the ton level, so that you can make a lot of batteries. So there's a scaling issue. And then there are some other issues as well, because there are a lot of other things goes into the battery, okay? And so that could also reduce the energy per mass, okay? It's not just the active material, you also have to add some backing and substrates. So those issues have to be solved. So at the end, how many miles can you really drive really depends a lot on what other things you put in there as well. So there are definitely a lot of engineering issues involved in this, making this into a real battery in a car. So what we did is just a proof of concept. Okay. So I would think it at least take a few years to make something that's possibly practical.
Thank you very much.